Today we are going to look at moving load analysis, and this moving load analysis video may be useful, or this video may be pertinent to those who have taken a course of bridge engineering or design of bridges, especially in either in undergraduate or as a graduate course. So what we will do today is we will perform moving load analysis in SAP2000, and we will compare the result that we obtained from SAP2000 with the result that we have got from Excel sheet. So here I have prepared an Excel sheet, and this Excel sheet generates the values of bending moment and shear forces for a simply supported bridge span of 25 meter. And the type of load that is moving here is the class 70R wheeled load. We will look at this load in a short time. What we have done here is we have used Excel VBA to generate these values of bending moment and shear forces. So what it does is, you can see here at different spans of the bridge. For example, for at 0 meter, at 3.125 meter, 6.25, 9.375, at these various spans of the bridge, as the load moves from one end of the bridge to another, it generates different values of bending moment and shear forces at these locations. And we have used coding here to calculate the values of maximum bending moment and shear forces in the table below here. So we will not go through this code for now, but let me just show you what we have done here. Let me delete these values in these cells. We have used a macro here, and we will use this macro to generate the different values of bending moment. So as I click on this move vehicle tab here, you can see different values of bending moment will be generated in this row here for bending moment. So let me just click here. You can see the values have been generated as the load moves from one end of the span to another. Similarly, for shear forces also, I can click here, and correspondingly these different values of shear forces will be generated in these two rows. So we will perform moving load analysis in SAP2000 and compare the values that we have got in this Excel sheet. So before that, let me open this IRC code, Indian Road Congress IRC 6 of 2017, where these vehicle loads are given as the type of live loads that we will be using for design of bridges. And particularly today we are concerned with this class 70R wheeled load. You can see the magnitude of the wheel load that is for class 70R. The axle load here are 8T, that is 8 ton here, 12 ton, 12 ton, 17 ton, 17 ton, 17 ton and 17 ton. And the distance between these axles are also given here. For example, if this 80 ton load or 8 ton means 80 kilonewton. 80 kilonewton load is the leading load, then the distance between this first axle and the second axle is 3.95 meter. Similarly, second and third 1.52 meter, 2.15 meter, then 1.37, 3.05, 1.37 and 0.91. This is the gap. So we are not concerned with the end distances here, rather we are only concerned with the distances between these axles. So this is the class 70R wheel load, and we will be performing the moving load analysis for this type of wheel load. So without any delay, let me go to SAP2000, which I have already opened here. Let me start a new file. So I'll go to File, New Model, Save Current Changes. I don't want to save them. So we will start with a blank template. That is, click on this blank here, and a blank template will appear. If you look at the bottommost right corner, then you can see the units of this file are kilonewton meter. So this is the unit that we need. If you want to change the units, you can just click here and change them. For now we are using kilonewton and meter. So let me just right click here and select on edit grid data. I will modify and show system here. I will add two grids in the x direction. The first grid ordinate will be 0, and the second grid ordinate will be the span of our simply supported span, which is 25 meter for now. Also I will add a grid in y data and z direction also, but I will not modify them since we are only concerned with here longitudinal analysis, and we do not need the grid data in y or z direction. So after defining the grid system, click on OK, click on OK. So the 3D view you can see on your right hand side, and for the left hand side I want to see a XY view, that is the plan view. So I will click on this XY view here. You can just zoom out here and see the 3D view on the right hand side. If something is lagging in your software, then you can change the graphics mode. For that you can go to options, graphic modes, and if it is DirectX you can change that to classical plus. So this is our bridge here. We will draw a frame section so that we can apply the loads here. For that, for now I am not defining any particular frame section. What I will do is I will just click on this draw frame cable option, and the default section here is FSEC1. We will see what this section is after some time. I will just draw this default section here from here to here, and then right click to come out of this draw mode. So what is this FSEC1? If you go to define section properties and frame section, this FSEC1 is our default section. Click on this modify show property and you will see that this is a I section. So currently why I drew this default section is that we are not concerned with the bending moment and shear forces generated due to dead load. We are only interested in finding the bending moment and shear forces due to the live load, and our live load is the vehicle that we just saw before, that is our 70R wheeled vehicle. So what I will do is, since I am not concerned with this section and also I am not concerned with the forces generated by the dead load of this section, what I will do is I will click on this set modifiers and I will change the mass of our section to a very low value, 0.0001, and also weight 0.0001, since I am not concerned with the forces generated due to the dead load. So click on OK, click on OK, and click on OK. Now after defining this span on which our vehicle will move, you have to define the vehicle, and you have also to assign that vehicle to this span, so that when we perform the analysis, that vehicle moves onto this span. So for that we have an option in SAP2000 which we do not have in ETABS. You can go to define, and we have one option here, moving loads. So in moving loads option, first we have to define the path, that is on which path our vehicle is going to move, and then we have to define our vehicle, and finally we have to assign this path to this vehicle, so that the software actually knows that the vehicle is to move onto this path. So what we will do is, first we will define this path. Since this frame section that we draw here is our path, first we have to know the name of this section. So to do that, let me just cancel here. First you can click on this set display option, and on this frame option, if the labels option is not selected, click on this label and click OK. You can see that the name of our frame is 1 here. So we will assign this 1 number frame section as our path. So go to define again, moving load and paths, add new path defined, give any name to the path. For example, I will just give this as PATH, and we have this option here, number 1 frame, which is our this frame here, and the center line offset is 0. Just add this, and this will be our path here. So the center line offset means if the vehicle is moving with some value of eccentricity with respect to the center of the beam here, or center of this span here, then we have to give this center line offset, because this center line offset will be responsible for generating additional forces in terms of torsion or any other force. But since we are not concerned with that analysis now, we are only concerned with longitudinal analysis. That means when the vehicle moves from one end of this beam to the other end, we will just leave the center line offset at 0. And another thing that you have to change here is the maximum discretization length. Maximum discretization length means, if you look at this Excel sheet, what we have done is we have coded this in such a way that the vehicle moves at a step of 0.1 meter. That means at every step of 0.1 meter, when this coding works, then the values of this bending moment and shear forces are generated at every interval of 0.1 meter. So what we will do is, the maximum discretization length is, we will put this at 0.1 meter, and then click on OK and OK. Now after defining the path, we have to define the vehicle. For that we will go again to define moving loads and vehicle. Add vehicle. Let us rename our vehicle as class 70R in bracket wheel. So the units will be this meter here, and first we have to give the what is the value of our leading load here. As we saw in our code here, our leading load is a 80 kilonewton load. So using this drop down menu here, select as leading load, and our leading load is an axle load of 80 kilonewton. So write here 80 and then add here. So after defining the leading load, all the remaining loads that are behind this leading load are at a fixed interval, that is fixed distances, as we can see in this diagram here. For that, now I will choose the option fixed length here. Firstly, let us look at this code here. We have 120 kilonewton, that is 12 ton load at a distance of 3.95 meter. So minimum distance right here 3.95, and since we have considered the fixed length here, the maximum distance option is not active, and the axle load is 120. Add. Again we have 120 kilonewton load at a distance of 1.52 meter. So minimum distance 1.52, and axle load is the same 120. Click on add again. You can see as we have added the loads here, these loads elevation will be generated just above this here. You can see the arrows that represent the loads here. Since we have defined 3 load up till now, 3 arrows are present here, and the length of this arrow is proportionate to the magnitude of our axle load. This smaller arrow is 80 kilonewton load, and the remaining 2 arrows are 120 kilonewton load. Now we have two 470 kilonewton loads, first at a distance of 2.13 here and 1.37. So 2.13, and the axle load is 170. Add. Again at a distance of 1.37, the axle load is the same. Add. And finally the remaining 270 kilonewton loads are at a distance of 3.05 and 1.37. So 3.05, the axle load is the same 170. Click on add. And finally at a distance of 1.37, axle load 170. Add. After doing this much, we have defined the vehicle here. You can see here 1, 2, 3, 4, 5, 6, 7. 7 axles are present in our class 70R wheel load. So after this, click on OK and click on OK. Now we have to assign the path to our vehicle, or we have to assign our vehicle to this path, so the software knows that the vehicle that we have defined is to move on this path here. To do that, we have to go to define and load cases. See here, dead and modal load cases have already been defined. Add new load case here. You can give any load case name. For example, I am giving it as moving load. The load case type that you have to select for this moving load analysis is, if you click on this drop down menu, you can see the option moving load here. So you have to select this load case type. So after you select this load case type, different options are available here. For example, now you have to select the loads applied here. The load that we will be applying to our path is class 70R, but our path definition is not available here for now. This path definition at this bottom of this sheet will be available once we have added the loads applied. So the vehicle that we are going to apply is class 70R. Scale factor we will use 1 for now, but if you look at the IRC codes, then you can find different types of factor that we have to use with the live loads. For example, the impact factor and other factors. So the minimum loaded paths and maximum loaded paths are the same here. Since we have only one span here, we will use minimum loaded path also as 1 and maximum loaded path also as 1. And finally, after doing this, click add here. So once you click add here, your selected path definition appears here. Since we have only defined one load path for now, this is already available here. Otherwise, you can see 2 or 3 load paths which are listed on this left hand side, and you have to select the appropriate load path and take it to this right hand side. So for now this path will be our loaded path. Just right click here, and after doing this your definition of load case data will be complete. Okay. Now before running analysis you have to assign the restraints to your support. Since this is a simply supported span, let me select this joint here first and go to assign joint restraint. This will be our hinged end, so select this hinge and click on apply, and the right hand side we will apply a roller joint. So click on this joint, select on this roller and then apply, click on OK, and you can see in this 3D diagram on your right hand side the joint that we have drawn at the two ends of our span here. Since this joint is not available to see for us on this plan view, you can select this XZ view, and if you select this XZ view, now we can see our joint properly in our plan view also. So now we have to run analysis. To run analysis, either click on this run analysis or go to analyze and then run analysis. Click on run now. The software will ask you to save the file. So I will save it now in our desktop for now by giving it a name, moving load analysis. So once our analysis is complete, now you can see the bending moment diagram here. This is a default value, and to see the stress diagrams for our choice, you can go to this display. After the analysis is complete, go to display, so forces or stresses in frame, cables and tendons. So currently we want to see the forces and stresses for our moving load case. First we will see the moment 33 value, and we want to see the values in our diagram, so this option show values is selected and then click on apply. So you can see that this is our bending moment diagram here. If you right click on your frame here, you can see the details. For example, currently the type of bending moment is our maximum bending moment that is being displayed here, 4633.45. If you look at our Excel sheet, we have calculated the bending moment at different values of our span here. For example, let me check in this 12.5 meter what will be the value of bending moment. So for that, select this option here, scroll for values, and then set the location to 12.5. You can see that the value of bending moment at 12.5 meter is 4628.6 kilonewton. And if you compare this with our Excel sheet, you can see 4627.4. So it is very near. So by comparing these two values also, you can be assured that what you have prepared in this Excel sheet is almost correct or entirely correct, because this difference is very much negligible, 4627.4 and 4628.6. Similarly, let me see at another place which will be 22.5 meter. Not 22.5, let us see it, 21.875. 21.875. So you can see the resultant moment is 2093 kilonewton meter, and on our Excel sheet is 1936 kilonewton. So you can see the difference between these two values is greater for this section here, 821.875 meter. So some differences may be generated when we are doing this analysis in an Excel sheet or when we are doing this in SAP 2000. You just have to make sure that whatever you have done while coding in Excel sheet is correct, and also when you are doing in SAP 2000 is correct. So this is the way to check for the bending moment and shear forces by performing the moving load analysis. Similarly, if you want to see for shear, you can select this shear 22 and then click on OK. You can see this maximum and minimum shear force diagram generated here, and the value is 795.08. You can see this 795.08 at 0 section here also. Maximum shear force at 0 is 791.048. That means near to the support or at the ends, the value of the shear force is the highest, and these two values are also comparable, 791 and 795. So in this way you can perform moving load analysis in SAP 2000. Thank you.